Welcome back to our next lesson. We're going to do a bit more chemistry following the grade 10 Australian chemistry curriculum. We're looking at valency, periodic groups, and a little bit of metallic bonding. Okay, I do draw your attention to the files that go with these recordings. There are a number of handouts and so on that are good revision activities and extension activities, so make sure you look at that part of the links that I've sent you. Here we are in our list. We're still in this third week of our chemistry course. Looking at this stuff here. And once again, we've got some nice little pictures from Chuck Norris. He only recognises the element of surprise. So what are we doing? We're going to identify the relationships between periodic groups and valency, what we call valency. So periodic groups, like I said last time, was those columns on the periodic table. Valency is whether we gain or lose electrons. That's the term that chemists use to describe how an atom will gain or lose electrons. That's important because that's the basis of chemical bonding or reactions. Any reaction usually is something to do with the valency and how the atom will gain or lose its electrons. A little bit about explaining what the properties of metals are, identifying them on the periodic table, and we've got a nice video here that I want you to have a look at. So let's have a look, talk about some of this. And there's a few concepts we haven't really mentioned before. When we look at our periodic table, like we've got down the bottom right corner there, we have the periods, which is why it's called the periodic table, and they're the rows that go across the table. But we also have the groups, and it's important. The groups is probably one of the most important parts of this table. So if we look at the first column here, that's group 1, and that's what we refer to as the alkali metals. And like I said last time, that's basically metals that are very, very reactive. So the question I've got here is, how many electrons do they have in their outer shells? So if you look at their atomic numbers, so the first one there is hydrogen, right there, has an atomic number of 1, which means it has 1 proton, which means it will have 1 electron, because the protons are positive, the electrons are negative, the negative charges balance the positive charges. So how many electrons has hydrogen got? He's got 1. So he will only have 1 electron. But if we look at the next one down, lithium has an atomic number of 3, so it must have 3 electrons. Recall last time that I said that when we draw these atoms, we have our nucleus in the middle, and then in the first electron shell or orbital, we put 2 electrons, so that would look like 1, 2, draw them opposite each other because they kind of repel each other because they're both negative. The next electron shell, you can fit up to 8, but how many is lithium going to have? He only has 1 more. So therefore he's got 1 in his outer layer. Let's look at the next one down. The next one down is Na, which is sodium. Sodium has 11 protons, so he must have 11 electrons. I've already drawn 3 on there, so if I keep drawing, I've got to get to 11. So it's 3, 4, 5, 6, 7, 8, 9, 10. I'm going to need another electron shell. I've drawn 10 little crosses, so how many do I need now? I need 1 more, so I'll put him just there. How many electrons has sodium got in his outer shell? He's only got 1. What can you tell, looking forward, about running down this group of alkali metals in that first column or first group of the periodic table? They will all have 1 electron in their outer shell. This is 1 electron sitting right out there on his own, and that tends to make them very reactive. So hence they all tend to be very reactive and release lots of energy when they react. So that's your first question. How many electrons do they have? 1. Question 2. How many electrons do the alkali earth metals have? Now the alkali earth metals is the next column, or group 2. So you can see you've got Be, beryllium, Mg is magnesium, Ca is calcium, we spoke about him last time, and so on down the group there. Now, if lithium had an atomic number of 3, beryllium's got an atomic number of 4. So he's going to have 1 extra. So he'll have 2 electrons in his outer layer. And all the way down that group, they'll have 2 electrons in their outer layer. So every one of these is going to have 2 electrons. All right. These group in the middle here, that's what's known as the transition metals. We'll just give them a miss for now, and we'll jump across to group 13, which is sometimes called group 3. All right. Group 1 had 1 electron in its outer layer. Group 2 had 2. So if we call this group 3, how many electrons do you think he'll have in his outer layer? 3. 4, 5, 6, 7, 8. Now, this last column here we refer to as the noble gases, and they're called the noble gases because they often are very unreactive. And think a couple hundred years ago when people started putting this stuff together, the nobles were seen to be better than normal people and hence didn't mix with common people. The noble gases tend not to react with other elements, so hence that's why they were called noble gases. How many electrons have they got in their outer layer? Well, it's group 8, so they have 8 electrons. There's your answer to that question there. Because that outer electron tends to be full, they tend not to react. But the halogens is that column right next to it. And that is it tends to be a group of gases, or if you look at it, you've got fluorine, chlorine, bromine, iodine. They're not always in gaseous form, but they often are. They tend to be not metals, is the point I'm making. They tend to have 7 electrons in their outer layer. So what they're itching to do is find 1 more electron to fill up that outer shell to make it full. So for example, chlorine here has 7 electrons in its outer layer. Sodium has 1. So what can happen is sodium can easily lose that 1 extra, give it to chlorine. Chlorine fills his outer shell, so he's got 8 in his outer shell. What happens then is chlorine has an extra electron, so he tends to be negative charge. Sodium has lost an electron, so he lost a negative charge, which means he now is positive. So the two of them will stick together, and that forms sodium chloride, which is table salt. So let's answer our questions and summarize all this. How many electrons do the alkali metals have? They have 1. How many electrons do the alkali earth metals have? 2. How many electrons are missing from the outer shell of the halogens? They are missing 1 because they have 7 out of the 8 possible. Noble gases all have 8. And it's called a periodic table because these rows are periods. That's another word for it. And it runs in this cyclic fashion. And there's our answers there. You can pause that and read that in a bit more detail if you like. So, metals. Now, the funny thing I haven't mentioned about the periodic table is you can see just there, metalloids are in that green colour, and that's these ones that run down the screen, just down there. Everything on that side we refer to as a nonmetal, and everything on that side we refer to as a metal. Okay? Think of your metals. You've got gold, silver, mercury, all these other ones like calcium and magnesium we refer to as metals, although they don't look like metals. In their pure form they often are. The only outstanding one is hydrogen, which is not a metal, it's obviously a gas, but it behaves exactly like the metals, and that's the best place to put him. So metals tend to be everything on this side of that little line that I've got through the table there. All right. So this is a good point to open up your textbook and refer to some of the stuff that's written there. But what you want to have a look at is some of these questions here. Why are metals good electric conductors? Why are they shiny? So what this comes down to is that metals tend to be good conductors because they tend to be able to lose their electrons quite easily. We often refer to metals as having a metallic lattice, which is kind of like if you have a piece of metal like this, you have a bunch of positive charged atoms. Whoops, there we go, like this. And mixed around that is this sea of electrons that can kind of flow easily. So there's all the electrons around here that can kind of move around these positive charged atoms. Because they can the electrons can detach themselves from the nucleus quite easily and flow around. They can move well. Hence, metals tend to be really good conductors of electricity because electricity is just a moving charge, which is moving electrons. That's really all it is. So when you hook this up to a battery or something, at either end, the electrons can flow through that metal quite easily. That's what makes them good conductors. The fact that their electrons can easily just sort of detach a bit from the nucleus. This tends to make them quite shiny, and they tend to be all similar. So when you look at pure substances like sodium and calcium, they tend to be a very shiny metal, like a piece of shiny steel. All right, so valency and nonmetals. So now we're looking at nonmetals. So the number of electrons that an atom either needs or has in surplus to have a complete outer shell is its valency. What these atoms are looking for is a complete outer shell. They want to fill their outer shell. So if you think about the alkali metals, like I said before, they've only got one electron in its outer shell. So it's very easy for it to eject a nucleus and get rid of it, and then whatever's left, it might be positively charged, but it's still a full shell. Think of our halogens over here. It's very easy to accept that electron and put it in their outer shell, and they'll fill their outer shell and have 8 electrons in the outer shell, because they all want 8 electrons in the outer shell, because that's stable. That's what the noble gases already have, which is why they tend not to react. So, metals, they tend to have a surplus amount of electrons, kind of like the case I just gave with the alkali metals. But for non-metals, it tends to be a deficit, okay? And they tend to want to get electrons from wherever they can, and they do it by reacting with a metal, taking that extra electron to fill their outer shell. So we tend to have a bit of a trend across the periodic table. As we go down the periodic table like this, the atom tends to increase in size because we're adding more protons, which means we're adding more electrons, and the whole thing just keeps building bigger and bigger and bigger. We keep filling more and more electron shells as we get more and more electrons. But the funny thing is, as we go across the period, the actual size of the atom tends to decrease. So this guy here is beryllium, this one's lithium. Beryllium is slightly smaller than lithium, so the question becomes, why is that? Because beryllium has an extra proton, one extra positive charge, it's going to attract the negative electrons a bit more strongly and pull them in just that little bit closer. So the overall trend that we've sort of exaggerated with this diagram here is, as you go across, they tend to get slightly smaller in size because you're adding more positive protons to attract the negative electrons closer into them. Although the electrons exist in those orbits, there's kind of a little bit of movement in that if you think of it that way. Got a little website at the top there that I encourage you to go and look at, where you can look at different aspects of elements on the periodic table. I want you to get that website, spend a bit of time exploring it, seeing what information you can find. It'll talk about all sorts of different parts about atoms, like density and so on, and have a check it out. Remember what I said last time? The periodic table stopped around about here somewhere or here somewhere when I was in high school. You can see they've extended it right out to the end there with all these extra elements that we've created. There's a little bit about electronegativity, which is that idea of the atom attracting its electrons towards itself. So as we go across the periodic table, the atom itself tends to get slightly smaller because more protons attract the negative electrons and pull them in closer. Okay, so we've looked at the groups in the table, the valency, or how they gain or lose electrons. We looked at the electron configuration. Remember, 2 electrons in the first layer and then 8 electrons in every layer after that. We want 8 electrons in our outer layer because that is more stable. And how do we do it? The nonmetals tend to be lacking some, and it's easier to add a couple to make up the 8. The metals tend to have only a couple extras, so it's easier just to lose them and have your outer shell full, and you give them to the nonmetal. That's the basis of how reactions occur. Have a think about what we've done today, and I'll see you next time. Thanks a lot.